Okay, guys. So last time we talked about solving polynomial equations. This time we're going to talk about polynomial functions. Remember the difference between a function and an equation. In a function, we've got a correspondence between two values. So we have x and y, or f of x. So a function as opposed to an equation. So a polynomial function looks something like this, where it can be to any exponent, right? So a quadratic is, we might have some constant here, 3x squared plus 5, a different one, okay? X to the 1 and then plus a constant, or it might be 3x to the 5th plus 4x to the 4th plus 7x squared plus 8, right? So generic form of a polynomial function. And because they're functions and I have x and y values, we can't solve them for one particular value like we can an equation. So our solution is a graph, right? Okay, so polynomial functions are smooth, continuous curves on the interval negative infinity to infinity. That means this is the domain for all polynomials. Their domain is always negative infinity to infinity. If your polynomial is an even degree, right, it has a range from whatever the bottom y value is up, or if it's an upside down one, right, up to the top. So you can either say negative infinity all the way up to k, or k up to infinity. Okay, so here's a couple of typical graphs. Notice this is a 4th degree polynomial. This is a 6th degree polynomial. The negative in front makes it upside down, just like the ones we've talked about before, just like the quadratics. And notice something, that all of these basically even degree functions, the outside, we're going to call that the end behavior, looks like a quadratic. Okay, the only difference is in these graphs and a quadratic is there might be some stuff going on in the middle, right? Some stuff going on in the middle. But the ends look the same. If you have an odd degree, right, they look like our cubic function, right? And as a matter of fact, some of these are cubic functions, but look, and remember we said this was going to be important and we'd talk about later? Well, here we are. This was the graph of just x cubed. Remember, f of x equals x cubed. But if you have some square terms and linear terms, some other terms besides just, x cubed, or, we had x minus 2 all cubed plus 3. But if I had some square terms and linear terms in there, that might make some wobbling happen in the middle of the graph. Okay, so the range of polynomial functions of odd degree is also all real numbers, negative infinity to infinity. And they look like cubes on the end, right? They all have that same cube shape, but they might have some stuff going on in the middle. Now, this one, if you've got a negative in front, then that cube is flipped over, right? So here's, you can see this is an actual just plain cube shape like we were talking about. This is a 5th degree, and it's still overall got that cube shape, but there might be some stuff going on in the middle. Okay? Okay. Here's where that little hump bit comes into play. Okay, the behavior of a graph at a 0 depends on the multiplicity of the 0. If there's a multiplicity of 1, in other words, just one solution, then it just goes straight through. I don't know why they have both of these angled. It could just come straight through the graph, right? But it just goes straight through the x-axis. If there's an even multiplicity, in other words, two values that are the same answer, it's going to touch, make a little flat spot, and come back up. In other words, it's going to make a little parabola at that value. And if it's an odd multiplicity, if you have 3 or 5 solutions that's the same number, it's going to make a flat spot, but then keep going, right? Come down, it'll touch and make a flat spot. And this is why the graph of f of x equals x cubed, it's important to have that flat spot there, because there are 3 answers really that's 0. So it has multiplicity of 3. 0 is a solution with multiplicity of 3. So these features of the graph are really important. Now this one, it's obvious you must do this, and this one it goes straight through, but it's these odd multiplicities we got to be careful of, and don't just draw your line straight through. Show the feature of that graph that it has a little flat spot there. Okay, really, I've already covered this. This is about the end behavior, right? So the turning points, here's if you have n, your biggest exponent, right? The term of greatest degree. If it's even, it makes a parabola shape. Of course, if your coefficient, the number in front of that term, is positive, it's going to open up. And if it's negative, it's going to open down. If the degree is odd, right, the biggest exponent is odd, it's going to make like a cube shape. If the numeral in front of it's positive, it's going to be the regular cube shape. It's going to be flipped if it's negative, right? Everything's upside down. This, instead of going up, will go down. This, instead of going down, will go up. Okay. Okay, so based on the end behavior, let's see if we can match these graphs to these functions. All right, so all I need to know is that this is going to look like on the end a parabola. I don't know what's going on in the middle. That's what we're going to be left with determining in a minute. We'll talk about how to find that. But I can tell immediately what's going to go on, what this is going to look like, because this is positive. It's basically going to be a graph that looks like this. So when I look down here, it's this one. This one has to be f of x. That's my only option. Okay, this one, because the degree is odd, it's going to look like a cube. It is a cube. There may be some stuff going on in the middle, but again, because it's positive here, then I know that the end behavior, I don't know what's going to happen in the middle there, but it's got to look like this. Oh, here we are. So this must be h of x. This is an even degree, but the coefficient's negative, so it's going to be an upside down parabola with some stuff happening in the middle perhaps. So it's this one, which means this one must be k, but again, it is because it's an odd degree, but because this is negative, it's going to be, instead of a cube like this, it's going to be an upside down cube, which is exactly what we have here. Okay, so just based on those two pieces of information, the degree and the sign of the leading coefficient, we can tell what's going to happen at the end of the graphs. So now all we need to do is figure out what's happening in the middle. Okay, so to graph a polynomial function, they never did tell us about our humps. So let me add one thing to this. Okay, so an nth degree polynomial, I'll just add it down here, put it somewhere in your notes, right? An nth degree polynomial has at most n minus 1 terms. All right, so think about this. Let's even just go back to a first degree polynomial function, right? This is a first degree, so n minus 1, 0, it has no terms, and we know that the graphs of these linear functions are lines. Think about a quadratic, okay? It can have at most one term, and yes, they either look like this or like this. A cube can have at most two n minus 1 terms, so it could look like this. 1, 2 humps, 2 turns, or like this. Right? Or it doesn't have to have any, but the most it can have is 2. So if I had a 6th degree polynomial, it could do this. 1, 2, 3, 4, 5. It could look like this. 1, 2, 3, 4, 5. It also could look like this, right? The most it can have is 6. But I know my quadratics cannot look like this, right? And I know a cube cannot look like this. This at most could be a 1, 2, 3, 4. So this at most could be a 5th degree polynomial. Okay. So keeping that in mind now, here's the steps of how we're going to graph these functions. First, we're going to determine the end behavior, right? Then we're going to find our x-intercepts. We know that when we need our x-intercepts, we set the function equal 0 and solve the corresponding equation. Determine the multiplicity and make sure that we do the appropriate mark at that intercept. Find the y-intercept, which means plug in 0. Find some extra points, right? Before we needed that extra point, we used symmetry, but now we'll talk about what kind of extra points we need, and then draw your graph through all those points. All right, so here we go. Now, this is a cube. So I know because this is odd and this is positive, my end behavior is going to look like this. All I have to do is figure out what's going on in the middle. Okay, so first of all, I'm going to try to find my x-intercepts, which means I'm going to set this equal to 0 because the x-intercepts is when y is 0, and the y-intercepts is when x is 0. So I set it equal to 0. I'll see if it'll factor, but it won't factor. If I factor out an x squared, I'm going to be left with 2x plus 5, and then over here when I factor out the negative 1, x plus 6. So it won't factor. So I'm back to our method from before. How do I find these zeros? Well, I need my p's and q's. So p is factors of 6. Q factors of 2. So my possible solutions are these numbers divided by these numbers. So 1, 2, 1, 2, 3, and 6. And then 1/2, 2/2 is 1. So 3/2 and 6/2 is 3. Okay, 3, 2, 1, 0. Make sure you don't have any missing terms. And then let's do our synthetic division. Let's see if we get any help from Descartes. Okay, I see it's changing here, and if I plugged a negative in here, this would be negative, and if I plugged a negative in here, it would stay positive, so no help this time. But it just takes a second to check, and it might cut our work in half. So let's try 1. 1 times 2 is 2. Add them together. 1 times 7 is 7. 7 minus 1 is 6. Woohoo! We have found 1. So I've got a point. And remember now, these are points that 1, 0. Okay? And then that makes this 2x squared plus 7x plus 6 equals 0. Okay, and so I need two numbers that multiply to give 12 and add to give 7. So that would be 3 and 4. Doesn't matter which order you write them in. It'll work either way. Okay, so I can factor out 2x. Let's put it right here so I can factor out 2x, and that leaves x plus 2. I can factor out a 3, and that leaves x plus 2. So then I have x plus 2 and 2x plus 3 equals 0. So I've got 2 more points. X is negative 2. So at negative 2, 0. And x is negative 3 halves. So negative 3 halves, 0. Okay, and then we need our y-intercept. And if I plug a 0 in here, it's just like with the quadratics. Hey, I can just look right here. Right? Don't forget that negative is part of that number. So then I also have the point 0, negative 6. Okay. So let's plot these points because I know that that y-intercept is negative 6. Maybe I'm going to go by at least 2's. We may even come back and change that. But let's see. So 2, 4, negative 2, negative 4. Okay, so I've got a point at 1, 0, a point at negative 2, 0, a point at negative 1.5, 0, right? Now, before I go much further, okay, I also have a point down here at negative 6, but I just want to make sure that this shape will go through these points, right? Just to make sure that I haven't made a mistake somewhere, and that looks good. That looks good. Okay, so now my extra points. So one thing I know is on the ends, I know this is doing this, and this is doing this. Okay, all I have to figure out is, does this go through here and turn up? Does it come way down here? Does it come past it? When I get points really close together, it just doesn't have much room to go very high. So that's fine. That's good enough. But let's try and plug in and do f of negative 1, just into my function up here. And it turns out the easiest place to plug it in is, because we will already have this thing factored. Let's put my factor here corresponds to that on here. Here's the entire thing factored, right? So if I were to plug in a negative 1 right here, negative 1 minus 1, this would be negative 2. And a negative 1 right here would be 1. And a negative 1 right here would be 1. Notice that's much easier than plugging in up here. Okay, I could have done synthetic division with negative 1. That also would have been pretty easy. But I can see this is negative 2, so that point is right there. If I needed a more precise graph, I would plug in 1/2 here. But we're not going to go to so much trouble that we have to plug in those fraction values. But I do want to get as accurate as possible, because again, it could go through here and down a little bit before it comes back up. But here's a pretty good graph. It's a good approximation anyhow. And so we can see what we mean now by extra points. I'm going to get points in between my intercepts, right? If I have room to do so. All right, let's try it again. Hey, look, on this one, they've done the complicated work for us. They have it all factored out for us so that we can tell our zeros. Let's look at end behavior first, though. This is an x squared term times an x times an x. This is a 4th degree polynomial if it were all multiplied out, okay? And it's negative, so the end is going to look like this. So I know that already. All I have to do is find out what's going on in the middle. Okay, so it's all factored for me. I know then that my zeros are x equals 1. One of them is x equals 1. That means that's the point 1, 0. One of them is x equals 3. So that's the point 3, 0. One of them is x equals -2, so that's the point -2, 0. Okay, so there's my 3 intercepts. Again, so far we haven't had any multiplicity, so I'm going to go ahead and draw those on here, and next we need our y-intercepts. Now, giving it to us already factored makes the y-intercept a little harder than typical, but it's not bad at all. All I have to do, because remember the y-intercept is when x is 0, so all I'm doing is plugging in a 0 here. So 0 minus 1, so I'd have a -1 there. 0 minus 1 is -1. 0 minus 3 is -3. 0 plus 2 is 2 squared is 4. So we have 3 negatives makes -12. So our y-intercept is at 0, -12. Okay. So maybe I'm going to make this go by 3's this time. Okay, so let's plot our points and see what we have. We have 1, 0, 3, 0, -2, 0, and 0, -12. So let's see if this shape can go through these points. Okay, if I came up this way, okay, now I've got a problem here, because if it turns around right there to go through here, this should have multiplicity. Okay. Oh, and it does. And it does. Right. So that's why it's nice to make sure your graph will fit in. Really, there's 2 of these that's -2, 0. So I've got multiplicity right here. So I got to remember it's going to make a little U shape. So perfect. Coming up, so I'm going to go ahead and draw that in. Makes a little U shape, goes through here, and then it could go through there and up through here. That's perfect. About the only thing I don't know, since I already have a point in between these intercepts, I need to know what's happening in between here. Does it just come like this? Does it come way up? What happens in between here? So I'm going to pick this value 2 and plug in, and let's see what f of 2 is to get my extra point. Okay, so 2 minus 1 is 1. 2 minus 3 is -1. And 2 plus 2 is 4 squared is 16. So 2 negatives, this is +16. So I've got another point, my extra point, at 2, 16. 3, 6, 9, 12, 15, about right there. All right, so I'm going to go ahead and put my end behavior in. I know what's happening on the ends. All I have to do now is fill in to go through the rest of my points. Look what a complicated graph. Isn't it kind of cool and exciting that we can do these complicated graphs by hand? Interesting. And now I have a very good approximation of what's happening with that graph. All right, let's try it again. Okay, this is a 4th degree again, so it's the end behavior is going to look just like a parabola. It's positive, so this time the end behavior is going to be going up. Now I need my x-intercepts. This won't factor, so let's find our p's and q's. So p would be factors of 8. Q factors of 3. So possible solutions would be these numbers divided by these numbers. So if I divide them by 1, I get the 1, 2, 4, and 8. Divided by 3, I would get 1/3, 2/3, 4/3, and 8/3. Let's look at Descartes. Okay, plus minus, so that doesn't help me. If I plug in a negative here, then it's going to be positive. If I plug a negative here, this will be negative, but a negative will be positive. Oh, if I plug in a negative here, it's going to be positive and a negative. So still no help from Descartes. 4, 3, 2, 1, 0. That's okay. Just do our synthetic division. 3, negative 7, negative 6, 12, and 8. Let's just try 1. 1 times 3 is 3. Add them together. 1 times negative 4. Add them together. 12 minus 10. 1 times 2. Not 0. So let's try negative 1. Negative 1 times 3 is negative 3. Negative 1 times negative 10 is positive 10. Negative 1 times 4 is negative 4. This is looking pretty good. 12 minus 4 is 8. Negative 1 times 8 is 8. Woohoo! All right, so I've got one of my x-intercepts at negative 1, 0. Okay, I'm going to try this and see if it'll factor, but I can tell from these numbers it won't factor, right? I can't factor anything out here. I could factor out a 4. It'd be left with x plus 2. So it won't factor, so I just continue my synthetic division with which number, guys? I hope you said negative 1 again. There might be multiplicity, right? So negative 1 times 3, negative 3. Negative 1 times negative 13, 13. 13 plus 4, 17. So no, not negative 1. So let's move to 2. We've already tried 1. If 1 didn't work in the first one, it won't work now, right? But we'd have already gotten it if it was one of our solutions. So let's try 2. 2 times 3 is 6. 2 times negative 4 is negative 8. And 2 times negative 4 is negative 8. Woohoo! We found another one. 2, 0. Now remember, I better get 4 of them, right? But now, this is a quadratic, so I can skip that and I can just try to factor it. Because we can solve any quadratic equation, no matter whether it's real number solutions or not, right? So I always want to stop when I get to a quadratic. I need 2 numbers that when I multiply gives me negative 12, and when I add gives me negative 4. So that's going to be negative 6x plus 2x, right? Okay, so if I factor out a 3x, that's going to leave x minus 2. And if I factor out a 2, that's going to leave x minus 2. So x minus 2 and 3x plus 2. That means x equals 2. Oh, we got some multiplicity going on here again. And x equals negative 2/3. Okay, and then let's just quickly look at our y-intercept. So I also have the point, not x, I also have the point 0, 8. The 8 is our y. Okay, so let's plot those points. Okay, negative 1, 0, 2, 0, 2, 0 with multiplicity, and negative 2/3, 0. All right, and then I have 0, 8. So let's make these go by 2's again. So 0, 2, 4, 6, 8. Now, let's make sure that shape will fit in here. Now, I know at this point I have multiplicity. So I know it's going to look like this because that end point needs to go up. And I know this end point is going, it's not going down, is going up also because of my shape here, right? All right, so let's see if it'll fit in. That means it's going to go down here and it can come back up and it can cross here and it can go in. Perfect, perfect. Let's just get that extra point right here, f of 1, in case it keeps going up before it turns, right? Now these are so close together, it can't go down very far. All right, but let's plug in f of 1. And once again, let's do it where it's all factored. That's by far the easiest place to do it. Or you could do synthetic division. As a matter of fact, let's just do the synthetic division. We had that earlier because we did one. So if you still have it on your paper, just look up to where you did 1 and you've got your value. I don't have it here. I erased it for the sake of room, but let's go right now. 3, -7, -6, 12, 8. And I need and I need 1. I don't even know what that would be. 1. Okay. 1 times 3. Okay. -4 when you add them. 1 times -4. -10. -10. So 2 times 1. So it would be at 10. So perfect example of why we need these extra points. It goes up a little bit more before it comes down. All right, so it comes up, and this is where it's actually going to turn, and then it's going to do our return there because of multiplicity. And let me caution you too, don't draw these too long because I don't know if it goes off over here or if it comes pretty well straight up. So just put a little arrow on a little short piece right there. And that's a very good approximation of that graph. All right, let's try it one more time. One more time. Hey, and they have the factored part done for us again. So nice. Okay, so what degree is this? 2, 1 more, 2 more. It's a 5th degree. This is positive, so it's going to look something like this. I just have to figure out what's going on in the middle. Okay, and so in the middle, you know, we haven't had one that had an odd multiplicity, so keep that in mind. That's what makes that flat place. But it's easy to see now they've got it factored already for me, that my zeros are, one of them is when x is 0, so the point 0, 0, and this has a multiplicity of 2. Don't forget to check your multiplicities. Then there's one where x equals 2 with multiplicity of 1, so it's just going to go straight through. And then x equals -3 with multiplicity of 2. So once again, I know, okay, it's going to have this right there at that point. Okay, and then to find our y-intercept, that's when x is 0. So if I plug a 0 in here, 0 squared, whoa, we already know what it's going to be, right? Doesn't matter what those are, multiplied by 0 plus, look, I had it right here. So the y-intercept is also 0, 0. It doesn't give me an extra point. All right, so let's plot these points. I have 0, 0. I have 2, 0. And I have -3, 0. All right, so I know my end behavior is doing this and this. And I know at 0, 0 and at -3, 0, right, we've got to have a hump, which means it's got to be this way if it came from below. Then here's my turnaround. It's going to do the same thing at 0, 0. So will that all fit in? It can come down here, and then here, and then there, and then go up. Perfect. Perfect. So now I need a couple of points. I need to know how low this thing goes and how low it goes on in this section. Ideally, if I wanted to be as precise as possible, I would plug in -1.5. But hey, right, these are just approximations anyhow. Let's just plug in -1. They've got it all factored for us, so that's easier, the easiest thing to do, right? Just plug in instead of as if before we were doing the synthetic division, we'd have to multiply all that out. But since it's all factored for us, -1 squared, and then -1 minus 2 is -3, and then -1 plus 3 is 2 squared. All right, so I've got, it's going to be negative, and I better get a negative or it's not going to fit my graph, so that's nice and reassuring. Okay, so this would be 3 times 4, so -12. Let's go by 2's again then. So I've got a point here at -1, -12, 2, 4, 6, 8, 10, 12. We'll say it's right here. And then let's do the same thing for +1. Okay, so 1 squared. 1 minus 2 is -1. And then 1 plus 3 is 4 squared. So this is -16. It's even lower. 12, 14, 16. Well, right, just so we don't have to redo our values. So this comes way down here, through this point, up here, turns around, and continues. Okay, and notice my ends are going in opposite directions because it's an odd degree. And again, I've got a very good approximation of that graph. Okay, awesome. Let me know if you have any questions.